Welcome, and thank you for coming this afternoon to today's seminar. Before we start, please be aware of the exit signs in case we need to leave on a sudden notice for whatever reason. And those that are on the internet, we strongly request that you consider sending in your questions for the Q&A, and the address is at the bottom at Coastal RM, that you send your emails at first opportunity so that we could have time enough on the air to take them. So with that, Dr. Yoon.
Thanks, Peter. Good afternoon, everyone. My name is Seungju Yoon from California Resources Board. I worked with the other project investigators, including Dr. Kanuk Samson, and as a project manager, and I worked with him for 3 years. And we have final findings of this project on the heavy-duty activity study. And Kanuk have done tremendous findings, and he will present a lot of good new information for supporting our programs and our policies. So this seminar is scheduled until 3:30, and first an hour or so, Dr. Boris Samson will go over his research findings, and then 30-minute question and answer will be followed. If you have any questions, please hold until the Q&A session. And if anyone who has the other question from the web, then you can send your question by email, listed on the other announcement. And if you have a cell phone here, and please put it on the mute. And now I'd like to introduce the Dr. Kanuk Samson. Dr. Kanuk Samson is the Associated Research Engineer at the College of Engineering, Center for Environmental Research and Technology, CSERT, University of California, Riverside. His research focuses on sustainable transportation, vehicle activity analysis, vehicle energy and emission modeling, intelligent transportation system, and connected and automated vehicle technology. Dr. Boris Samson is a key member of CSERT's Sustainable Freight Research Initiative. Dr. Boris Samson was recently appointed to the Vice Chair of the Vehicle Technology and Activity Subcommittee of the Transportation Research Board's Transportation Air Quality Standing Committee. Dr. Boris Samson.
Thank you, Dr. Yoon, and good afternoon, everyone. I hope you hear me okay. It's my great pleasure to be here and present to you the research finding from the projects that we just recently completed. This is a very exciting project that has produced a lot of information that we will go through together today. And just start off with some background. As you know, heavy-duty vehicles, especially those run on diesel, are major contributor of NOx and PM emissions in the state. And in terms of emission control from these vehicles, the 2010 standard has tightened the level of NOx and PM emissions significantly. And in response, engine manufacturers mostly use selective reduction technologies, selective catalytic reduction technology to control NOx emission in order to meet the 2010 standard. Now, SCR is typically SCR need to be at a certain temperature in order for it to be effective in terms of NOx conversion. As you can see in this figure, which is a NOx conversion efficiency curve from one commercial SCR technology. So the exhaust temperature need to be about 200 degrees Celsius for 40% NOx conversion efficiency. And if you want something like 90% or 80% or above, then the exhaust temperature need to be at least 300 degrees Celsius. Now, when heavy-duty vehicles operate in real world in use, we don't know if the SCR temperature can be maintained at that high level for all the time. Because as you know, heavy-duty vehicles, they serve a variety of vocations from long haul all the way through package delivery and others. And the different vocations, vocational use would result in different operating patterns, which may impact how SCR perform. Let's look at some example. On this slide, we have a plot of speed profile of one truck in blue line and the SCR inlet temperature in red line. So as you can see at the beginning of the trip, when the vehicle was just started, the SCR temperature was low and tried to build up. Oh, by the way, the green horizontal line there is the 200 degrees Celsius threshold for 40% NOx conversion efficiency. We can see that it takes a while before SCR temperature could build up to above that threshold. And once the vehicle was in operation for a long time and start engaging in long idle, we can see that here is about 5 minutes idle. The SCR temperature dropped significantly to the point that it went below 200 degrees Celsius. And then after the long idle, it starts moving again, and that is okay until this portion where it seemed to be creeping at the speed lower than 15-20 miles per hour for an extended period. And again, SCR temperature dropped significantly. This time it didn't drop below 200 degrees Celsius, but it's still a significant drop. And so this is an example of how SCR temperature can vary significantly during the real-world operation of a truck, especially a diesel heavy-duty engine. So that's why we conducted this research project with the following project objectives. The first thing is to collect real-world vehicle and engine activity data from heavy-duty vehicles in California. And this is across multiple vocations, all the way from line haul to drayage to construction, because we want to understand how the different vocations would be different. And once we have the data, we wanted to characterize the activity profile in terms of number of starts per day, idling time, soak period, etc. And the third objective is to identify fraction of the operation where SCR temperature might be low, and then the SCR may not be as effective in terms of controlling NOx emission or converting the NOx emissions. And lastly, with the data that we collected, we also like to develop driving cycle that are specifically for each vocation for possible use with chassis dynamometer in emission testing. One thing I like to note is this project has benefit from research partnerships with other organizations. Here on the chart, we see that ARB funded the research, fund UC Riverside to conduct the research. And during the project, UC Riverside established a cooperative agreement with the US EPA, who has contract with Eastern Research Group. So in this research partnership, what happened is we were able to expand the scope of our data collection. Originally from only 20 trucks with ECU parameters, we were able to collect ECU parameter from all the 100 trucks and also collect additional information about the fleet themselves. And this has resulted in a database of vehicle and engine activity data that will be useful for many years to come. In terms of data collection, again, we collect real-world in-use both vehicle and engine activity data from 90 trucks in California, and each of them we collect data for a minimum period of 1 month. And we use a tiny data logger. It's about your palms. The size is about your palm. That contain both GPS receiver and ECU reader. And the data logger is configured to log the data at 1 hertz or second by second. In addition to the standard GPS parameter that you get from typical data loggers, we also configure the data loggers to log more than 170 ECU parameters. So it's a huge data set. In typical vehicle activity data collection programs, at most you get about 20 or 30 parameters. Here we are talking about 6 times the size of the data per second. In addition to the data from the vehicle, the loggers, we also collect the information about the trucks themselves, the make, model year of both the chassis as well as the engine, and the weight, the odometer, so that we can use those to inform the analysis. This slide is a little busy. Basically, it's a summary of our vehicle samples. At the beginning of the project, we worked closely with ARB staff to identify the vocations of interest. We base the sampling of MFAC, where MFAC has 27 heavy-duty categories in the model. So we try to kind of match the vocation that we're going to collect data from with those MFAC categories. In the end, we decided on 20 different vocations as listed on this slide. And we estimate about 5 samples per vocation, and that gives you a total of 100 target trucks. Excuse me. During the program, we try to recruit trucks from different fleets and try to install the loggers. For some vocation, we were able to recruit more than 5. For some others, we were not able to recruit any. So in the end, we successfully recruited and installed a total of 102 data loggers. But some of them were lost or incomplete for various reasons. So eventually, we have a complete data set for a total of 90 trucks. One thing I'd like to note, the comment column just kind of note how many data loggers were lost for each vocation. We have 2 versions of data logger. One is equipped with Wi-Fi, and the other one is equipped with cellular modem. And basically, with Wi-Fi loggers, if they are lost, then all the data is gone with the logger. But with cellular modem, some of the data were still available because the data have already been transmitted to our data server. So that's something to keep in mind if you are to perform future data logging program. In the next few slides, I show kind of pictures of example vehicles from each vocation. Yeah, most of them look like a standard Class 8 tractors, like the one that do line hauls, drayage. In terms of construction truck, we have both dump trucks and water truck. We have cement mixers. For food and beverage distribution, again, these are standard tractors. We have airport shuttle fleet, refuse, as well as urban buses. Just a note about urban bus, these are not conventional diesel, they are diesel hybrid electric. At the beginning, when we try to recruit fleet, we set out to recruit trucks that are 2010 model year or newer, because they are most likely to be equipped with SCR. But there were a few vocations where we were not able to find any participating trucks or vehicles. with that particular specification. So um, we just accept the fact that some of the vocation may have different field or vehicle technology. We also have express buses, and again, these buses run on CNG and not diesel. We have quite a bit of fleets from public agencies that do different kind of work, such as freeway or sweeping, and we also have one utility repair fleet that participate in the data collection. So in the end, we have huge amount of data. Is almost actually over 100 gigabyte of data that we have to sort through, receive, process, sort through, and then analyze. So on this slide, I'm list the major data processing step that we went through. First is the data conversion. The data loggers log the data into two binary files. One is from the GPS receiver and the other one is from ECU or CAN reader. So we have to put those two files together in the software that provided by the data logger vendor, and it converts the data files into the binary files into text limited files that can be further analyzed or processed. Once we have that text limited files, we conduct a process called map matching, which is basically to identify the road type that each data point was on. In this research, we only look at three broad road types, either freeway, non-freeway, or ramps. And then after that, we put the data through a substantial data quality assurance process, where we look at different kind of errors and filter data, make corrections as necessary. I will talk about detail of the data quality assurance in the following slide. And then after that, we can start looking at identifying trips from a stream of long data files. And again, I have a separate slide on that. The fifth step is trip origin and destination cloaking, and this is mainly to protect fleet and driver privacy and confidentiality. So in this step involve removing the latitude and longitude information from the data files for every single trip. So we still preserve the speed and other information about the engine. The only information that was removed was latitude and longitude. And lastly, we aggregate all the data into kind of individual files, one file for one vehicle. Let's look at some of the details on data quality assurance. One thing that we found is that there was a lot of issue with timestamp, and timestamp is very critical because that's the key information that allow you to sort the data, right, chronologically, and understand the difference in activity patterns. So we have two sources of timestamp information. One is from the internal GPS clock, and the other one is from the GPS receiver, and the other one is from the internal clock of the data logger. And we have found that the timestamp of the GPS receiver is more reliable, and we use that as a primary source. The next big thing about quality assurance is vehicle speed. And again, this is very important when we try to understand how the truck moved and was driven. And we again have two sources of speed information. One is from the GPS, and the other one is ECU reported view-based speed. And we have kind of gone through both speed data, both set of speed data, and come to a conclusion that GPS-based speed is more reliable, just because ECU-based speed has many more types of errors. And what we did was we correct each speed data and then later combine them into one composite vehicle speed. And I have some example plots to show just to demonstrate the corrections as well as the combination of the two speed source. So on this slide, it shows the issue with ECU-based speed data. So you see that, oh, by the way, it's a little busy, and I apologize for the font size. But the key thing that I like to point out is if you look at this light blue stripe, is the raw ECU-based speed, and you notice that from time to time it will jump to a very high number, and that's usually happen when the connection with the CAN was lost and the ECU is not reporting any information. It will just default to that maximum values. So to correct that, basically you can just connect the two data point pre or after the bad data, but that will result in something like this, where if you look at the green lines, which is GPS-based speed, the truck was doing a lot of driving, right, with some acceleration. But if you rely on ECU-based speed and just connect the two dots during the missing data period, then it looked very unrealistic. This is another example with ECU-based speed data issue. In this case, we see a lot of instances with, again, similar type of erroneous data where the speed, ECU-based speed show very high values. And we were able to just make correction by connecting the 2 points as I explained earlier in the previous slide. And the missing data is small enough that you can confidently make connection without doing a long projection of what happened in between. But after you do the data connection, and when you compare that to the GPS-based speed, which is in green lines, you will notice that the corrected ECU-based speed will have, from time to time, some unexplainable offset. It will jump up from the trend and then drop down and then jump up again. And we cannot explain this. And this is part of the reason why we think that GPS-based speed is more reliable. But GPS-based speed data has issue of its own, especially when the number of satellite is low, because obviously GPS rely on satellite signal. And at the beginning of the trip, when the data logger just starting up, it would need some time to acquire the satellite signal. And that's where we rely on ECU-based speed as the main data source. Now, this slide shows a case where both source of speed data provide a good match between GPS speed and ECU-based speed. Okay, so those are some details about data quality assurance that was done on the dataset. And the following step after the quality assurance is to identify trip. I should point out that the nature of how the data logger works is that once the key is switched on, basically the data logger is power up and it's created the data file and start writing the data right away. The engine may not be on, but the data file has been created and start logging data. Now, when the engine is switched on, that's when the RPM kick in, go to 600 RPM or around that level. And then the truck was driven, so the engine operated for a certain period of time. then the engine is switched off, RPM drop to 0, and the key may not be turned off right away, and the data file doesn't end there. The data file keep going until the key is switched off, and basically there is no more issue there to log. Then the data logger closes the data files. So what happened is, in a data file, you have a period where the engine was not in operation. If you look at the data file as a trip, then basically you overestimate the period of time where the engine is on. And that impact the soak period of the engine, that impact the engine idle time calculation. So in this project, it's very interesting that we have not only the GPS data, but also data from ECU, especially RPM, so that we can identify trip as the period from engine on to engine off. So in identifying trip, we use RPM of 300 as the threshold to separate between engine on versus engine off status. And this is kind of selected because the typical idling RPM is around 600 to 800 depending on the engine. And we have seen some noise in the RPM data. And instead of using 0, we just say that 300 is a good threshold to prevent noise in the data and also to differentiate between idling RPM versus engine off. So with this logic, then we can identify trip where the trip represents the period of engine operation. And each trip is assigned a unique trip ID. A few notes on this is that some data files may not contain any trip. For example, if the driver switch on the key without turning the engine on and then switch off the key, so a data file was created, but there is no trip. On the other hand, which is that happen more often, one data file may contain multiple trips because the driver turned on the engine without switching the key off and then turn the engine back on. So all these kind of nuance was taken care of during the trip identification process. Another thing that we has to handle unexpectedly is that there were instances where data files were created accidentally because of the interruption of data connection with the ECU. So as I mentioned earlier, if the data logger lost connection with ECU, which typically happen when the engine is switched off, it's close the data file, right? So in some instances, that interruption happened and the data logger was fooled into believing that the engine was turned off, so it closed the data file. And once the connection was reestablished, it create a new data file. So technically what happened is you have two data files that are supposed to be for the same trip. We detected that during the latter part of the project and had to go back and make correction to that. So this is a good example where you see that you can, I'm not sure if you can see it in detail, but basically this data file has the ending speed, vehicle speed of 10 miles per hour and RPM, ending RPM at around 1200, which is not possible, right? The engine cannot be turned off like that. On the other hand, the following file has the starting speed at 10 miles per hour and the starting engine RPM at 1100. So it's very obvious that these two data files supposed to be continuous and be a single data file. But this issue has been corrected and the analysis was done on the data that has taken care of all the issues that I described. Okay, so next we will start looking at data analysis. A few notes that I like to make before we go into the result. One is that we only use data for weekday, and this is because MFAC is a weekday model, so it only accounts for trips during weekday. And there's a couple of things that need to be defined before we go into the result. One is idle trip, and this is defined by ARB as a trip with speed less than 5 miles per hour and with distance of less than 5 miles. I apologize for the typo. That's supposed to be 5 miles. So these idle trips could happen at, for example, warehouses where the driver turn on the engine not moving and then turn off, maybe to just to get air conditioning or to listen to the radio. There is also another technical term called extended idling event, and this refers to a continuous activity segment within a trip where the second by second vehicle speed is consistently less than 5 miles per hour for a total duration of longer than 5 minutes with the total distance of less than 1 mile. So all these conditions has to be met for that part of activity segment to be considered extended idling event. And this is not meant to represent something like getting stuck at traffic light. It's more to represent activity where, for example, a drayage truck idling at the port while waiting for the container and things like that. Another important thing that need to be differentiated and understood is the concept between calendar days and operation days, because a number of statistics that we analyze is on a per day basis. We log data continuously for a period of a minimum period of 1 month, but the trucks were not used every single day during the data collection period. Some days they were not used at all, and that's why we make differentiation between the calendar days versus operation days. In the next several slides, we will go through some of the results, and I'm just going to point out some interesting finding in each of the slides. The first one, we look at the average vehicle speed. Basically, this is total distance over the entire data collection period divided total operation time. We have two set of plots. One is the blue bars, which include idle trips and extended idling events. Now, the orange bars do not exclude any of those, do not include any of those. So as you would expect, if we include the idle, you will see that vocations such as drayage would have very low average speed, or vocations that run mostly in urban area like refuse, airport shuttles, and express bus all have a pretty low average speed as you would expect. And then those that do line hauls will have higher average speed. And after we exclude the idle trip and extended idling event, obviously the average speed would increase, and the amount of the increase depending on how much idle activity the trucks had, right? So for example, for drayage, a significant amount of time was spent idling. So after we exclude the extended idling event and idle trips, the average speed of drayage truck almost double. The same is true with cement mixer here. The average speed almost double after excluding idles. Operating time by road type. So the different colors, there are 3 road types that we identify in this data set: freeway, non-freeway, and ramps, represented by 3 different colors. And again, this is as expected. Some vocation operate purely on non-freeway, like airport shuttle, refills, and to some extent urban buses. And line haul, we have more time spent on freeway. So these are as expected. On this slide, we're looking at operating time by mode. And mode here, I refer to vehicle operation mode, whether it's in braking mode, idle mode, coasting, or cruising. And again, the different modes are represented by the different colors. And again, it's kind of intuitive where you see that line haul trucks have the most time in cruising mode, and then the vocations that spend most of the time on non-freeway road, such as refills, airport shuttle, and urban buses, would have more fraction of time in idle mode. Another one that has a significant amount of idling time is cement mixer, as well as utility repair. And again, these are intuitive because these trucks cannot do that job while idling, right? Even though a lot of these results are intuitive, but I think the fact that we have quantitative information about them is still useful. On this slide, it shows number of starts and idle trips per operating day. Again, I would like to point out the differentiation here. This is per operating day, which means the days where the truck actually operates or is used. When we look at the number of starts, some of them are unrealistically high. For example, Drayage, Northern California has more than 25 starts per operating day, which is surprising. Even line haul out-of-state trucks have more than 15 starts per day. I couldn't wrap my head around that. But then when we look at number of idle trips per operating day, now we start to realize that a lot of those starts are actually just turning on the engine and then turning off without moving at all. Maybe the driver needs some air, he needs to charge his cell phone, or for whatever reason. So if you subtract the number of starts per operating day by the number of idle trips, that's when you get the sense of how many trips each vocation of trucks are making on a per operating day basis. Aside from these basic statistics, we also analyze the data in terms of distributions. There are multiple types of distribution that we derive. On this slide is distance by speed distribution. What fraction of the distance happen at the different speed. So on the horizontal scale, we have speed bin from 5 miles per hour all the way to 90 miles per hour. And this is a two-dimensional distribution where on the vertical axis, we have time of day from midnight to the next day. On this particular example is the distance by speed distribution for Drayage truck in Northern California. And when we look at the heat map, the pattern of the heat map, we can see that it has a very defined operating hours, right? It's a 7 to 4 operation daytime operation, and most of the operation happen at low speed, around 10-15 miles per hour. And when we look at the area where these trucks operate, we see that they spend most of the time in and around the port. All the warehouses that they visited are close to the port. That's why it kind of explains that operating pattern, low speed, 10 to 15 miles per hour, because the truck rarely get on freeway. Now, on this slide is the same type of distribution, distance by speed, but for drayage truck in Southern California. And again, I'm gonna go back to Northern California, Southern California. So now you see that the heat map has totally different pattern. And for Southern California, it's pretty much all day operation. There are some activities during nighttime, and most of the miles happen at relatively higher speed. Actually, it happen at highway speed, 50-55 miles per hour. And part of the reason is that in Southern California, there is an off-peak pricing program that encourage drayage trucks to go to the port during off-peak hours to alleviate congestion around the ports. So that's why there are activities during nighttime. And the fact that it has more miles at freeway speed probably contributed by the two reasons. One is that nighttime, usually freeway is not congested, and also that some of the facilities that these trucks visited are further out from the ports, and these drayage trucks have to get on freeway in order to get to those destinations. So when we look at this type of distribution for all the vocation, we can kind of roughly classify the 20 vocations into whether it's full day operation or part day operation, as listed in this table. It's interesting that even for line haul, for different fleets, they may have different operation patterns. Some fleet doing it all day, some fleet have specific hours. Another type of distribution that we look at is soak time distribution. Soak time is basically the period from the moment the engine is turned off until when the engine is turned on again. And it has impact on the catalyst temperature. The longer the soak, the cooler the engine and exhaust, and then that could impact the NOx conversion. So on this plot, it's soak time distribution, where we have a range of soak period from 5 minutes all the way to 720 minutes. Again, it's a two-dimensional distribution where the vertical axis represents the hour of day. And for vocation with specific operating hours, we see a very clear pattern where in this example, the municipal trucks has overnight soak for most of the time, because the engine was turned off around 4 or 5 p.m. and then it wouldn't be started again until 6 a.m. the next morning. So it always has overnight soak that end around 6 a.m. in the morning. In contrast, for some vocations, such as beverage distribution truck, the soak time distribution is more random. You see that the heat map is all over the place, and the peak soak period happened to be 10 to 20 minutes. And there is rarely overnight soak because it's probably running all day long, making short stops. It's kind of interesting to go through the different distribution for each vocation and try to tell a story about what they were doing and try to make connection about their vocational use and then how their activity pattern looks like. Now, in the next few slides, we will look at one specific parameters that we were able to log from ECU, which is SCR temperature. Again, we talk about the importance of this SCR temperature in terms of NOx conversion efficiency. So we will look at how real-world SCR temperature profile look like. On the top plot is for line haul out of state, and the profile look like a bimodal distribution. One has a peak at around 280 degrees Celsius, which is good, pretty good. And you probably can guess that that's when the truck was cruising on highway. Another peak is around 100 degrees Celsius, and that's probably when it's idle or spending time on non-freeway roads. Still, about half of the total operating time, 56% to be exact, SCR temperature of line haul truck was lower than 250 degrees Celsius. And that's still quite a significant amount, right? Now, if we look at drayage, this is a drayage truck in Northern California. One thing to note about this truck is that it's from the same fleet as the line haul out of state trucks. So they have very similar engine size and model year. It's just that it was used for drayage service rather than line haul. And we can see a contrast in the real-world SCR temperature profile where the peak is around 110 degrees Celsius, and about 90% of the operating time has SCR temperature lower than 250 degrees. So quite a contrast, and this is clear evidence of how the truck is used will have a significant impact on real-world SCR temperature profile. On this slide, we will look at two more example vocations. One is refuse, and as we saw in the activity results, refuse trucks operate mostly on non-freeway road, spend a significant of time in idle mode. But somehow, these trucks were able to maintain relatively high SCR temperature with a peak of, with the mode of 240 degrees Celsius. We were not able to explain why. It might has to do with the engine, the thermal management of the SCR itself, or other reasons. But yeah, this is very interesting that for a vocation where you would expect low SCR temperature, these trucks were able to maintain pretty good SCR temperature. For utility repair, this is another vocation where you would expect a lot of idling and probably a large fraction of low SCR temperature. And this one doesn't surprise us because the mode is around 150 degrees Celsius with 75% time under 250 degrees Celsius. Now, if we look at across all the vocations and look at how much fraction the trucks were under a particular temperature, here we show only two threshold either 200 or 250 degrees Celsius. You see that quite a bit of operating time for these trucks were below those thresholds. If we take 200 degrees Celsius, it's about 11, I think the blue line is about 11 to 87%, depending on vocation. Now, this slide is a product of this slide, fraction of operating time under specific temperature, and multiplied by the efficiency curve, NOx conversion efficiency curve here. This is for one example, commercial SCR. So if we take, for example, 40% conversion efficiency for temperature 200 degrees Celsius, 75% efficiency for 250 degrees Celsius, 90% conversion efficiency for temperature 300 degrees Celsius, and so forth, and apply this curve to the real-world SCR temperature profile. It gives this result, okay, which is the estimated total engine out NOx reduction by SCR. And a couple of important things to note. These results based on that particular example SCR NOx efficiency, conversion efficiency curve. It's not that every single truck in this study use that particular SCR technology. Some may use one that can be more effective even at a lower temperature. So if we make that assumption, under that assumption, and if we look at the result, we find that the NOx reduction from SCR could vary widely from 16% to 69% depending on vocation. Another important thing to note here is that it doesn't mean that NOx emission inventory of heavy-duty vehicles is underestimated by this much, because when SCR is low, it usually happens when the engine has low load, and typically under those conditions, the engine out NOx is not as high as when the engine has more load on it. So the impact on the total NOx emission inventory from heavy-duty vehicle would be lower than what we see here. Okay, now we're going to switch gear and talk about the last objective of this project, which is to develop vocation-specific drive cycles for different, for the heavy-duty trucks. And on this slide, we will talk about the procedures that were used to develop the cycles. The first step was to do data reduction. At the request of ARB, the cycles to be developed should not include idle trip and extended idling events. So we have to remove those activity segments from all the data files, which means that if those extended idling events occur between the trip, now we start to break the trip up into what we call vehicle activity strings. Now within vehicle activity strings, there could be multiple stops where the vehicle speed comes to zero. So we want to cut the vehicle activity strings into short, what we call snippets. So whenever the vehicle speed comes down to zero, we cut it so that there is a unique activity from zero speed to the next zero speed that represents one snippet. Once we have all these snippets, and you can imagine it's a large number of snippets because we have a lot of trips already, and we cut them every time the vehicle speed come down to zero. We can start creating cycle by tying these snippets together, and this could result in multi-millions number of combinations. So basically, each snippet can be a cycle by itself, and any combination represent a unique cycle. And all these multi-million possible combinations are referred to as candidate cycles. Now, among all these candidate cycles, we only select one that we consider the most representative of the entire activity data population of the truck. The selection process rely on two concepts. One is called vehicle operating mode distribution. Operating mode here is defined by the MOVES model developed by US EPA as unique mode where emissions characteristic of the vehicle is statistically significant from other modes. So there are a total of 23 modes as defined by the graphic on the slide. Now, in MOVES, the emission calculation is done by multiplying the distribution of operating mode with the emission rates for each operating mode, right? So if you know that the vehicle spend X amount of time in mode 1, then you can multiply that by the emission rates in grams per second for that mode. And you can do so for all the operating modes and then sum them up, and that gives you total emissions. What this means is because emission rates for each operating mode is pretty much fixed, it means that if you can generate a drive cycle that has the same operating mode distribution to the distribution of the data population, you have a good chance of estimating the total emission per unit time as if you measure emission throughout the data population. I know it's a little bit confusing, but I hope the report will have a better explanation that you can go through. Look like we hit the hour mark, and then I'll try to wrap up the presentation so that we can start taking questions. In terms of drive cycle result, we develop for each of the vocations, but in general, they can be grouped into 4 broad groups. One is mostly highway cruising. Another one is mixed driving of freeway and non-freeway. The third one is mostly transient driving. And the last one is mostly creeping. So in terms of concluding remarks, again, we successfully collect real-world activity data from trucks and analyze them in terms of activity pattern as well as SCR temperature profile. And we found that activity pattern for trucks in different vocations could vary greatly, and not only by vocational use, but sometimes also by geographic area. And based on the assumptions that we made, we found that the engine out NOx reduction by SCR could range from 16% to 69% depending on the vocation. And drive cycles were developed that can be used to test trucks in specific locations on chassis dynamometer. And I think what is probably the most important product of this research is the data set that result, right? It's a huge data set that we just started to analyze and try to understand how these trucks are operated, how their engine and emission control system work, and there could be a lot more analysis that can be done using this data set to answer different questions from technology and policy perspective. On this slide, I list a few recommendations for future research that could be just simply collect more data from additional vehicles or from additional types of vocation to looking at characterizing real-world SCR temperature profile, all the way to using this data to determine feasibility of electrification of some of these trucks. Last but not least, I would like to acknowledge several agencies and persons that contribute to this research. First of all, ARB for the funding, and also EPA for the technical support and the cooperative agreement that provides supplementary resources. UC, ITS, PTA also chip in with some supplemental fund so that we can finish the data analysis. And there are a number of contributors that are listed on the slide. And last but not least, all the participating fleets that allow us to log data from their vehicles. And that's the end of my presentation.
Thanks for that presentation. You mentioned that you had identified times when the ECU connection was dropping out based on when the last line had a high vehicle speed and the first line had a slow. And I was wondering if maybe this is happening times when it's idling, and that could explain why you have a lot of idle starts for the long haul operations. I just wondered if there's another way if you could look for maybe times when there's a short time distance, a short time duration between the two, or maybe when you lose a connection, you don't get a complete line of data from the ECU. I don't know. Is there any way you might be able to identify the same situation but without the vehicle speed criteria?
Yeah, in addition to vehicle speed, we also use engine speed. So, for example, in that particular example, the engine speed dropped out at around 1200. So that's clearly not during idle. And also we found that most of the dropout are within 30 seconds. And we look at how much distance the vehicle could have traveled in that period of time, and compared to the distance calculated by latitude and longitude, and they are within reasonable range. Yeah, right, yeah. Yes.
I noticed that you took a month.
I have a question. Oh, is this a follow-up from the same question?
No, I'm sorry.
Okay.
This is,
Someone's ahead of you.
Okay.
Oh, okay. Would you like to speak first?
Sure. This is Professor Frank from UC Davis and